A spoonful of wine goes into the water glass. Stir it, then send a spoonful back. Which glass ended up more contaminated? Picture a late evening with two glasses standing on a table. On the left, red wine. On the right, clear water. Exactly the same amount in each. Someone playfully picks up the spoon, lifts a spoonful of wine, and pours it into the water glass. A quick stir blends the color, and the clear water turns a pale pink. Now take an equal spoonful from that pink water glass, and return it to the wine glass. Once that round trip is over, the level in each glass is exactly what it was at the start. But the contents have changed. Both glasses have lost their original purity. And here someone makes a bet. The water in the wine glass or the wine in the water glass, which is greater? The problem appeared in the late 19th century, in a classic book of mathematical recreations by the English mathematician W. W. Rouse Ball. Martin Gardner popularized it in the mid-20th century, and Lewis Carroll is said to have been fond of it. Coffee and cream, 2 barrels, 2 beakers, the costume changes but the skeleton is one and the same. Now let's restate the problem without a trace of ambiguity. Pour in a spoonful of wine, stir, and send back a spoonful of exactly the same size. As much came back as went out, so after the two transfers both glasses hold their starting volume again. There are 3 options. Let's just say the answer is the cleanest of the 3. Choose one right now in your head. Remembering your first instinct makes what follows far more fun. This figure captures that short round trip, one frame at a time. Follow it from left to right. In the last frame, the two glasses stand at exactly the same level. That single picture holds the key to the answer. Most people lean toward the two amounts being different, and there are several reasons to think so. The first trap: we sent over pure wine the first time. The first spoonful is 100% wine, but what comes back has already been watered down. Strong going out, weak coming back, so it feels as if more wine is left in the water glass. But this confuses concentration with volume. Strong or weak is a question of color. The second trap: the idea that the second spoonful is almost all water. The wine carried over by the first spoonful gets heavily diluted in the big water glass. So very little wine comes back. The wine feels trapped in the water glass. The third trap: the feeling that stirring harder changes the result. How hard you stir changes the mixing, so surely it changes the answer too. A bigger spoon, a smaller glass, surely one side gets the advantage. The fourth trap: the feeling that an exact answer requires a calculation. You think you have to multiply and divide the volume of the first spoonful, the volume of the glass, and the dilution ratio one by one. All 4 intuitions are plausible, and all 4 stumble in exactly the same place. We keep being pulled into a story about concentration, what is in the spoon and how strong it is. The real answer never looks at concentration at all. It follows straight from one much simpler fact. Words keep tangling us up, so let's break the liquids into beads and count them. Say the wine is 80 red beads, and the water is 80 blue beads. 1 spoonful holds 20 beads. Now let's replay the bet, step by step. First spoonful: we scoop 20 beads from the wine glass into the water glass. The wine glass is still all red. So the 20 beads we moved are, of course, all red. The water glass now holds 100 beads. Second spoonful: we stir the water glass well, then scoop 20 beads back into the wine glass. In the water glass, 1 bead out of every 5 is red. That's 20 out of 100. So the 20 beads we scoop up hold about 4 red and about 16 blue. In the water glass, 4 of the 20 red beads that came over have now gone back out. That leaves 16 red beads. And the wine glass now holds 16 blue ones. Count them yourself in the picture. The gold-rimmed beads, the outsider color, come to 16 on both sides. The coats count comes out the same. Both sides land on exactly 16 beads. But why exactly the same? Let's look at that second spoonful again. Of the 20 beads scooped up, only 4 are red. Blue fills the other 16 places. The less red comes back, the more blue fills the gap. 2 sides of the same spoonful. What if only 2 red came back instead of 4? Then 18 red stay in the water glass. Then 18 blue cross over into the wine glass as well. Exactly symmetric. Whatever spoonful you scoop, the 2 numbers move together, hand in hand. Now let's stop counting beads and see it all at once. Let's stare at just one glass, the wine glass. The wine glass is full at the start, and just as full at the end. The level ends exactly where it began. That one simple fact decides everything. The volume in the glass is exactly what it was at the start. Meanwhile, two things happened in that glass. Wine went out and water came in. An unchanged level means the liquid coming in filled exactly the space the departing liquid left behind. Any less and the level would have dropped. Any more and the glass would have overflowed. So the water that entered the wine glass equals the wine that left it. Only as many new guests sit down as there are empty chairs. Let it be the water that came in, and X the wine that went out. Then it equals X. Now let's add a second fact. Where on earth did the wine that left actually go? There are only two glasses on the table, and nothing evaporated or spilled. There is nowhere for it to vanish. So every drop that left is inside the water glass. Call the wine in the water glass B, and B equals X as well. Two quantities equal to the same thing are equal to each other. So A and B are exactly equal. Done without a single multiplication. All we used was a ledger of volume. Whatever leaves, that much comes back in. It is the smallest and most elegant specimen of the kind of thinking physicists call conservation. Let's check it with numbers. A glass of 80 milliliters, and a spoon of 20 milliliters. On the left, the blue band at the top of the wine glass is the water that flowed in. On the right, the red band is the wine that flowed in. The two bands are exactly the same height. Both are 16 milliliters. The original liquid filling most of each glass doesn't matter. All we're asking about is the two bands on top. Here is the hardest thing in this puzzle to believe, and for that reason the most beautiful. Read the argument again and you'll see we never once asked how well the liquid was stirred. We only counted the volume in and the volume out. Whether the liquid was strong or dilute never came up. Stir it carefully, stir it carelessly, or don't stir at all. The answer doesn't change. Stirring changes the concentration and nothing else. It cannot change the fact that both glasses return to their original volume. Extreme case 1. Suppose you never stir at all and the two stay apart like oil and water. Then suppose the second spoonful is pure water. Each side ends up with exactly one spoonful. Extreme case 2. Suppose that, by luck, you scoop back exactly the wine you just poured in. Both glasses are restored exactly as they began. The wine in the water glass is 0, and the water in the wine glass is 0. No mixing at all, a perfect undo, or anywhere in between, the two are always equal. Because every empty seat left by a departing local is filled exactly by an arriving guest. And this is where the second trap dissolves, the one that says the second spoonful is almost all water, so only a little wine comes back. If less wine came back, then exactly that much more water went in, and the two cancel exactly. Drop the stirring to 0, make the spoon bigger, run 10 round trips, the difference is still 0. Stirring only changes how contaminated each glass gets. It cannot touch the fact that the two are equal. A good insight always runs past the fence of the problem that produced it. Let's test it with a few variations. Suppose we move the spoon not twice but 10 times or 100 times. Even with spoons of every different size going back and forth, as long as each glass ends at its starting volume, the answer is the same. The argument never once counted the steps. It looked only at the level at the start and at the end. Send with a big spoon and receive with a small one, and the final volumes usually don't match, and then the equality breaks too. Still, what matters is not the size of the spoon, but whether each glass came back to its own starting volume. Stir sloppily or don't stir at all. Mixing changes only the concentration. It never touches the ledger of volume. The starting amounts can differ. Even with twice as much wine as water, nothing changes. The two glasses don't have to hold the same volume. The wine glass only has to return to its own starting volume. Spill a few drops along the way or let a little evaporate, and the final volume no longer matches, so the equality breaks. How much you have to correct depends on which glass lost what. So wherever the equality breaks, it is always where the volume failed to come back. The spoon, the glass, the stirring, the number of round trips, none of it is essential. The only essential thing is the return of volume. Instead of arguing it out in words, we handed the job to a machine. Spoon size, number of round trips, degree of mixing, all shuffled every run. With a single constraint, every run brings both glasses back to their starting volumes. We tracked 4,000 scenarios. On the left, all 4,000 points land on the green diagonal without a single exception. On the right, the axis is measured in trillionths of a milliliter. All that's left is rounding dust. As much comes in as goes out. That single line is one small facet of a deep framework the sciences all share. Mathematics and physics have a name for this kind of argument, finding an invariant. Grab hold of the one thing that never changes and you get to skip everything in between. Here, it's the total volume in each glass. Physics calls it a conservation law. In a closed system, the total mass and the total charge never change. Our table was a closed system too, and the wine had nowhere to disappear to, so the answer came straight out. Chemical engineering puts it even more directly. What comes in equals what goes out plus what accumulates. If the final volume equals the starting volume, the accumulation is 0, and then what came in is exactly what went out. One round trip of the spoon can be written as a linear transformation that redistributes probability. Conservation of volume gives that transformation a symmetry, and it echoes the steady state of a Markov process. But the only tool we actually used was a single one-to-one correspondence. And now the finale. The wine in the water glass and the water in the wine glass. Exactly equal. Big spoon or small, one round trip or 100, it stays equal. There is one condition. Each glass comes back to its starting volume. That is why this puzzle is so loved. It lines your intuitions up in a row, then knocks them all down with a single sentence. Try it at a cafe with your coffee cup in the creamer. Once the level comes back, the answer is already in your hands. The cream in the coffee and the coffee in the cream are exactly the same amount. One footnote: the wine/water paradox only shares the name. It is a probability paradox about the principle of indifference, an entirely different animal. Good mathematics often invites us, instead of calculating, to take one calm, steady look. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.